I remember. Which day was that?
18. All right. So just a reminder, your project proposals, 2 lines basically, are due today. I know many of you have already submitted them, which is good. Some of you have asked me about papers, and I either said, yes, this sounds good, or I said, maybe you should look at this other paper. I said, oh, maybe you should just look at something completely different. And people have come back and said, what about this? And so far, at least for the people who've talked to me, we've been able to come to some resolution fairly quickly. Yes.
When you say submit as a team, does that just mean identifying your other team members?
Well, the thing is, the way the submission is supposed to work is that it's by project group. So if one of the members of the group submits, it gets submitted for both. I don't know if that's been the experience of people so far. For those who've already submitted, did you both have to submit, or did just one of you submit and it automatically showed up, or anyone?
You just submit and it will automatically show up.
So anyone in the group can submit it and it works fine, yeah. Because the way it's set up, you don't have to both do it separately. I think yours is submitted, Jimmy. I think yours was submitted.
Okay.
I think I should check, but I think it was. But go check and see. If either of you did it, should be fine.
All right.
So yeah. Yeah. So I mean, and again, I created a few more project groups just in case. Like I said in the note announcement I posted today or yesterday. You know, even if you are a single person group, which I don't recommend but allow, you should try to make sure that you are in a project group just for administrative purposes. It'll be easier that way. Okay. Because a couple of you were a single person who just submitted directly. I mean, it's fine. It was a recorded submission, but just try to be part of the group. Any other questions? So you probably have also noticed that the second homework has been posted. It's on the longer side, but it's on the longer side also because there's a lot of explanatory material inside the homework itself. I was writing out the solution, and for the most part, if you use the definitions of the Markov, Chebyshev-Shanov, just the way they're written, and with the examples that we showed in class, you shouldn't have too much trouble working out most of the examples. They're more or less straightforward applications. There's maybe 1 or 2 questions where you think a little bit, but it shouldn't be too bad. But that's what we have the forums for, the office hours, and so on. So get moving on that. Someone had trouble compiling the homework. It's the same as last time. You just need the class file. Maybe you didn't copy the class file over from your previous one, but if you did, it should work. If you have any errors, just again post them on the forum, and I can probably debug it. I don't think there should be a problem. Given that you were able to compile it for last time, it's pretty much the same thing as this time. There's nothing different as far as I know. Any other questions about that? Yes?
Just like with the progress report that's due at the end of October.
Yes. You're jumping ahead. Okay, but anyway, yes, go ahead.
I just got curious, is there a certain amount of progress you're expecting?
I will explain. So I'm going to do a lecture where once all the dust settles with the submissions, I'm going to do a lecture where I try to explain what I expect to see in the report. So I'll spend a large part of the single lecture just on that. I'll give an example of how, I'll take a paper and just give an example of how you might go about attacking it. And that'll also answer the question of what I would like to see by the end of October.
Okay.
Any other questions? Okay, so approximations, TSP. Any questions? So how are people reacting to this sort of material and approximation so far? I'm just curious, do you have any questions? Do you have any thoughts, observations, complaints? How is it, what are your initial, these are probably things you've not seen before or only vaguely seen before. So I'm curious to know what your reactions are to some of this material before I continue. Anything, good, bad, ugly, whatever. Anyone? Nothing? No reaction at all? It's all easy, all good. Well, the easy part we'll find out, there'll be an assignment coming. So. Any other thoughts? Okay, so if you recall from last time, we were talking about the traveling salesperson problem, and we ended up with a 2 approximation to the problem. And the algorithm that we were using last time was basically, So what was it? Does anyone remember the algorithm for sort of a two? For the TSP, do you remember what we did? What is step one? Yeah? So step one was find a minimum spanning tree, which is an easy thing to do. Hopefully you all know how to do that. Okay, that's step one. Can you remember what to do next? Yeah?
Duplicate all the edges.
Duplicate all the edges. So, okay. Okay. Step three.
Find an Euler path.
Sorry?
Find an Euler path.
Find an Euler path. Okay. Step four.
Short circuit.
Short circuit or shortcut, I guess. So what does that mean? Can you explain that? What does it mean to shortcut?
You would want to take the paths that visit unique vertices without visiting one more than once.
So if you do end up on the Euler path visiting something that you visited before, you just skip it and you move to the next and keep skipping till you find something new. So shortcut by skipping previously visited nodes, right? And I'm going to put here a metric, which means that the distance function is assumed to be a metric, right? That's otherwise this doesn't make sense. So we also said that we could analyze this algorithm and give it to approximation. And roughly speaking, the observations kind of work like this. We found a minimum spanning tree, and we knew that the MST cost is less than equal to the optimal cost, because the optimal path is a path, which is a tree. Therefore, another tree would be even better. Right? We duplicate all the edges, so our cost multiplied by 2. By duplicating all the edges, we guaranteed that all degrees were even, so we could actually find an Euler path. Otherwise, we wouldn't have been able to find one. And then we short-circuited, and that only reduced the cost. And we were allowed to do this because of the triangle inequality. So the triangle inequality allowed us to do this, and as a consequence of doing it, we reduced the cost. Right? And this allowed us to conclude that the cost of the tour that we get, the cost of the path, is combine those two things up there, less than equal to 2 times the optimal solution. And that was our proof. Yes?
Just wondering, I remember on the project guidelines, you referenced the paper like geometries of graphs.
Yeah.
Is the triangle inequality like an example of the geometry of a graph?
Not quite. You're putting a metric structure on a graph by doing this. I think one would argue, well, I would argue that geometry implies something even more. In particular, in that paper, you were taking a graph and putting making the nodes into points in a Euclidean space, such that the distance between 2 points in the Euclidean space was somehow related to the shortest path distance in the graph. So we were taking the graph and making the metric structure of the graph a geometry by putting it in Euclidean space, which is what I mean by geometry. So it's different. But we are transferring something which is originally a topological concept, a graph, which is a very topological notion. Things are just connected, and putting a distance structure on it and giving it a metric structure. So putting a kind of a frame on it. So this is often something you do in this kind of work, where you take some structure, you put some new structure on top of it that gives you new insights, and then you can learn something. Yeah.
So we know that the traveling salesperson problem is NP complete.
It's NP complete, it's not in general, it's always NP complete.
It's always NP.
Well, unless you're on a path, which is
So my
true.
question is, when we have this restriction that we have to do the triangular inequality, is it still NP complete?
Yes,
Right.
yes. This is a good question, and yes, it is in fact true. That the traveling salesman problem is NP complete even if you have a metric structure on the graph. In fact, yeah. The original proof of the TSP requires merely unweighted edges in the graph. So yeah, but it's a good question. It's valid to ask that question because then you say, well, maybe I made the problem so easy, I don't need to do it. It's like solve it exactly. That's not the case. Okay? So you could end the story right here. And this is a good story that, there was this problem which was impossible to approximate, as we talked about earlier. And once you threw in a little bit of information about the distances, you restricted the distances in some way, in a way that was not terrible, it was reasonable. You suddenly went down to something that's quite good. But in fact, you can do even better. And once you throw in that extra twist, you get to a heuristic called the Christophanides heuristic, which was proposed in, I think, 1975. And for the most general version of this problem, is still the best known result for the traveling sales problem. It's not, we don't know any better than that, which is kind of surprising and interesting. And it's just one little extra twist to this that allows you to do this. And it shows you also how sometimes it's good to have more than one lower bound to play with to reason about what your algorithms do. So to understand how you can improve this, there is one step here which is incurring your cost. So when we say, okay, why are we getting a 2 approximation? If you look at the algorithm, where is that 2 approximation, where is that 2 with the 2 approximation appearing? And this is a good question to ask yourself when you're looking at your project paper as well. You'll see certain bounds. You'll say, okay, where is that bound showing up from? If you look at these steps, where is that 2 showing up from? Yeah?
In step 2, duplicate all the edges.
Duplicate all the edges. Why are we duplicating all the edges?
So that we can find a Euler path.
Why do we want to find Euler path?
So we can visit all the vertices.
So you can visit all the vertices. So to visit all the vertices, all we know how to do right now is to construct an Euler path. To construct an Euler path, all we know how to do is double all the vertices to make the graph of even degree. Because we know that any graph where all the vertices have even degree has an Euler path in it. Okay. Is there potentially a way to make the graph Eulerian, to make it have an Euler path? In other words, to get to step 3 without doing step 2 as much as we're doing it? Can we do it in a less wasteful way? And this is the question that extra heuristic, the Christophanides heuristic, seeks to answer. Can you be a little bit more clever about duplicating the edges to get an Euler path without actually duplicating the edges? Okay. So here's the point. So remember, the point is, so the problem here that we just face is, in order to improve the 2, okay? This is the problem we have here. And so the question is, how do we do this?
Could we find all vertices that have just one edge and duplicate, or an odd number and duplicate one of the edges? Do something like that?
So the problem that you're observing is that the problem here is vertices of odd degree. Right? Because you want all the vertices to have even degree. Of course, you just need to add one edge to a vertex of odd degree to make it even. So let's draw a tree. We computed some spanning tree for the graph. Maybe it looks like this. Maybe this is my spanning tree for the graph. Let us mark down all the odd degree vertices. So there's this one right here. And there's this one right here. And then there are all the leaves. How many of them are there? In this case, there are 8. And as you maybe have a counter, I think I've covered this in discrete math as well, it's so-called the handshake lemma. The number of odd degree vertices in a graph is even, just by a counting argument, because the total degree is even, and the number of, if you add up all the even degrees, they're even, so the total number of odd degrees has to be even as well, right? So the number of odd degree nodes is even, which suggests something to us. Our goal was to make all the odd degree nodes even, and the way to do that is to add an edge to them. But since there are an even number of them, maybe we can pair them up. Right? So maybe we can pair them up by saying, oops, sorry. So pair up all degree nodes. So maybe we do something like this. So we say, let's pair up these two. Let's pair up. I'm going to add an edge here. Okay. I have now added 4 edges to my graph. The graph is now Eulerian by definition, because I have made sure that every odd degree vertex is now even. This graph will admit an Euler tour. Everything else will work. I have also added fewer edges, potentially, than I added for doubling all the edges. Right? Maybe. Fewer. I don't know if they're less costly. So the real question I have to ask myself is, by doing this, instead of just doubling all the edges, have I improved my situation or not? Is this any better? And the goal, of course, is to make sure I do something less than twice the MSD. Okay. Is this problem? So, is where we are right now in this thinking process clear? That we've got some idea, we have some way of doing this, we just don't know how good it is. Okay. All right. So, let us now make the following observation. Right, definition. We just took every pair and we made it. So this is a matching, right? A matching is a set of edges that are all disjoint and the connected base. Right? In particular, so let's call these edges that we've added, let's call it M. And let's say M star equal to the optimal cost, actually, let me, the minimum where minimum cost matching is, well, I'm going to talk more about how to compute such matchings, but the minimum cost matching is the matching on the graph of minimum total cost, where the cost of each edge is just the distance between the two things. So, cost of an edge equals to the distance between endpoints. Okay? So a matching in a graph, edges that are disjoint. The cost of such a matching, sum of the costs of all the edges. Each edge cost is the distance between its endpoints. So I want the minimum cost, let's say I want to find the minimum cost one. Let's assume that the matching I find M in my previous thing was in fact the min cost matching on those odd degree vertices. So let's say that M was the min cost matching on odd degree vertices. Okay? Then we can immediately say that M is less than equal to, or the cost of M. Right? Because I'm comparing the minimum cost matching on some subset of the vertices to a min cost matching on all the vertices in the graph. So clearly this has to be less than that. Because I'm not using all the vertices. And every time I add a new edge, I have to pay for it somehow. Okay, but what does this have to do with anything? I want you now to consider the TSP tour itself. Okay? So let's look at the actual tour. So let's look at the optimal TSP tour. Let's just pretend it's a cycle for now. Now, on this cycle, there is a matching by taking this one, this one, this one, and this one. Right? Yeah. So let me just mark off this one. So there's a matching here, 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 and here. Since it's odd, I'm going to miss one anyway. So this is the best matching we can find. There is also a matching that looks like this. Right? There are two matchings on this tour. Yeah? And what can we say? That the green cost plus red cost right? Because you have a cycle and you have two of these things, right? So what does this tell us? If you have two things that add up to a number, one of them must be less than or equal to half that number by generalized pigeonholes or whatever you want to call it. Right? So in other words, we can say from all of this that one of the two matchings is less than opt, but one of the two matchings is in fact a matching. So the optimal such matching is less than that, so we can say that so do you see the steps here? Remember when we said that the MST was a good lower bound for the traveling salesman tour? Because a path is a tree, and so a best tree is better than the best path. What you're saying now is that this path here encompasses two matchings in it. Not just one, two. One of them has to be less than the other one, and that one has to be less than or equal to half the total cost. But that one is a matching, so the best matching has to be even better. A very similar reasoning to the way we applied for the tree, but now we're applying it for matchings. But because we have two of them, we get that factor half. Okay? But that's it. We're done now. Because what we're saying is that the algorithm costs now, just like before. So the algorithm, the cost of a solution, the cost of our tour, is equal to an MST cost plus a matching cost. Because that's what we had to do to create the graph that was Valerian. And short-circuiting never increases the cost anyway, so we don't care about that. Well, this was, we already argued, is less than equal to opt. This we already argued is less than equal to opt over 2. So the overall cost of the tour is less than equal to, and this is called the, I mean, it's not really a heuristic, but that's the name of the thing. And this gives us a 1.5 approximation to the metric TSP, not a 2. And the trick again here, and if you look at the notes, there's an example there involving what is called make span. So the problem I didn't talk about, but it's in the notes. It's the same idea that sometimes if you have a lower bound is what you need to show that you can get an approximation for a problem, but sometimes having 2 lower bounds that work in different situations, or can work together in this case, actually helps you even, because you can reason more carefully. Yeah.
So on the previous page, was the way we defined a matching, I'm a little confused on how you reasoned about there being 2 types of matchings in that example graph.
Well, every cycle has, the first edge, third edge, fifth edge, or the second edge, fourth edge, sixth edge. So let this in this form. I'm saying look at the actual tour, don't look at the graph. Look at the actual final optimal tour you get. Right? Let's see what properties it has.
Okay.
I can observe that it contains 2 matchings inside it. If I had an algorithm to compute matchings, it would find potentially one of these things. One of these things is sufficiently small. Therefore, the matching I find, which is the best one, can be no worse than that one. But that one is already less than opt over 2. So the best one is going to be even more, could be even more than opt over 2. It'll be no more than that. Yes?
Suppose you had an even number of vertices and you're then completing the cycle and using that as one of your edges in your matchings.
Yeah.
That missing edge could be very expensive, right? It's not, it could be the cost of the entire tour, that missing edge.
But if that edge is so big, then one of the matchings contains it, that matching will be expensive, yes?
Yeah.
Then the other one won't, right?
The other one won't, but how do you know that the other one is now less than or equal to opt over 2?
Because together they sum up to the, oh, you're saying that the optimal cost had not included edge in the first place.
Right.
So yes, so as a technicality, it's actually easier to reason about this whole chain of arguments in terms of the cycle. Because a cycle is bigger than a path, and a path is bigger than a tree. A path has more cost than a tree. The whole argument works even if you pretend this whole thing was a cycle instead of a path. So you can do this whole, it's cleaner to do reasoning with a cycle. But it also works. In that case, if you want to find the optimal TSP cycle, then you are going to pay for that edge. And not just, if you want to, in other words, get back to the beginning, then you will pay for that huge edge in the beginning. So it sort of works. Other questions? Yeah.
So did you say that this heuristic was general, like it can apply to other problems?
This trick?
Yeah.
Yes. Generally speaking, if you can come up with multiple lower bounds that work in different settings, then you can say, okay, when this lower bound, so lower bounds, a lower bound on the optimal solution is usually good under certain circumstances, but can sometimes be bad depending on the input. You can say, for example, okay, the MST is always less than equal to opt, but maybe it's really below the optimal solution, in which case it's a bad lower bound. You want a lower bound to be as close to the true answer as possible. So if you remember the picture I drew, right? So let me draw this picture here. So our reasoning about approximation says the following. This is the optimal solution. Let's say we're minimizing again. So this is cost. This is the optimal solution. We don't know where it is. We don't know what the optimal solution is. We have some algorithm whose cost is somewhere here. It's worse than opt, but we don't know how much worse than opt. But what we do know is that we have some lower bound that's here. and we can measure ourselves with respect to the lower bound. So if we're only so far away from the lower bound, we can't be any worse away from the optimal solution, because the lower bound is by definition better than the optimal solution. And so that gives us a reasoning for our relationship to the optimal solution. Now how good, if the lower bound, this is so a good case, would be, this is my algorithm, this is my opt, and this is my lower bound. Why is that? Because then the error in sort of comparing myself to the lower bound instead of the optimal solution is not much. A bad case would be this case, where I'm comparing myself to the lower bound. The lower bound is much worse than much lower than the optimal solution, so I'm not getting a good read on how good I actually am. I could be really close to optimal solution. So an even worse case would look like this. This was my algorithm here. This was my optimal solution. And my lower bound was way down here. Because I don't know where the optimal solution is, I'm comparing myself to the lower bound and say, okay, maybe I get a factor 5 approximation or something. But really I was dead on. And I didn't know that. And I couldn't prove it. So what you want is a lower bound that generally is always good. It's close to optimal. You can't always get that. So some lower bounds are good for certain situations, some lower bounds are good for other situations. So if you can get multiple lower bounds that kind of cover your bases, right? Then you can make sure that the max of all the lower bounds is close to the optimal solution. And this will all start making a little bit more sense once we talk about linear programming and duality, which we'll get to in a little bit later in the course. Yeah.
It's just a general question. I'm used to like lower bounds existing on the other side of optimal.
On the upper side?
Well, you have an optimal solution, but you don't really know what it is necessarily. And how are you getting such a lower bound? Like, are you just saying, well, we could do it in constant time, but not really having a proof for that?
So you're saying, how can I do better than optimal? Is that your question?
Yeah, I guess, naively. How can you, if you know there's an optimal solution.
How can you be going below it?
Yeah.
Because that lower bound is not a solution. It's just a number. For example, traveling salesperson tool. I said the MST is a lower bound. The minimum spanning tree is not a tool. I can't use it to solve my problem. But the value of the spanning tree is lower than the value of the optimal solution. And the spanning tree is easy to compute. So the lower bound is something that's not a real solution, obviously by definition. But it gives you a number that's guaranteed to always be less. And yes, your lower bound could be 0. Right? That's fine. It's a lower bound. It's useless though, because it's in this kind of situation.
Okay.
What you want is a lower bound that tracks your optimal solution well. Right? And that's where the skill comes in the art, if you wish, of approximations, coming up with lower bounds that work. And I think someone asked us last time, right, is there some generic way to do this? And there is. It's via linear programming. So when we get to linear programming, we will see there's a generic way to produce lower bounds automatically. You don't have to think as much as you do in these kind of special one-off cases. Other questions? Yes?
How do you know that the solution that you have is optimal, so that you can actually know that there's a lower bound?
You don't know your solution is optimal. You don't know anything about your solution. All you know is that you have your solution, you computed this lower bound, and because of the way you designed your algorithm, you have a way to compare yourself to the lower bound. That's all. So for example, again, back to the case of the minimum spanning tree, we said that our algorithm is going to compute a minimum spanning tree, it's going to double the edges in the easy case, and it's going to compute an answer from that. So we know that our algorithm cost is at most twice the minimum spanning tree. That's all we know. But we know separately that the minimum spanning tree is less than the optimal solution, just by reasoning about it. And so putting those two facts together tells us, okay, we're no worse than twice the optimal solution. So we actually don't know they're optimal, we just have a relationship to the lower one. Other questions? Yes?
So then, on our final answer where we say the cost of the tour is less or equal to 3 halves of the optimal solution.
Yes.
So that's an upper bound, right?
Yes.
Okay. So
Because less than equal to, so it's...
right.
Yeah.
So I mean, does that fit like anywhere in, so would that basically be A in the case of these graphs?
So we're saying that the distance between here and here is at most a factor of 3 halves. because the distance from here to here is 3 halves. Yeah.
So is there any sort of like tricks or anything that you can do if we say we're within 3 halves of the optimal solution? So divide our answer by 3 halves kind of thing.
Well, if you do that, then you get an answer that's, well, that'll give you a lower bound on the cost of the optimal solution, but they won't give you an actual solution. Our algorithm actually gives us a tour. It says, here, take this tour is within a factor 3 halves of optimal. Yes, and so by dividing by 3 halves, you already know, okay, I know my optimal solution is at least this much, but it could be anywhere in that range. Right, so for example, to say what you're saying, so you have an algorithm result here, okay? This is my algorithm result, and this is basically algorithm divided by 3/2. This is my cost, right? So now we know for sure that the optimal solution is somewhere in this range. But we don't know where. It could be here, could be here, don't know where it is. All we know is that within a factor of 3 halves. That's why this is an approximation algorithm. It gives you some range where you believe the answer to be. But it doesn't tell you any more. Does that make sense? So approximations are fundamentally imprecise, right? This is the imprecision. You have some kind of range. And you're never going to, for NP hard problems, you're not going to be able to do much better. Maybe you could do, if you're very smart, you get better than 3 halves. No one's figured out how to do this yet. It's been 40 years. Speaking of which, I didn't mention this because this has only happened once in 7 years, but I should mention this. You're all choosing your project sort of ideas and you're looking at papers. If any of your groups is able to read one of these papers and come up with a new idea or an improvement or some extension or something that's non-trivially different from the paper that I deem to be, potentially submittable, you will get an A on this class regardless of your homeworks. So I've said this every year for 7 years and it has happened once, last year. But that's my guarantee. And so it's not impossible. It has happened. Before I wasn't sure it would happen, but it can happen. Yes, you had a question.
What was that?
Huh?
What was the time?
There was a paper on basically covering a polygon by rectangles, and the group came up with a new idea that we actually wrote a paper. We haven't been able to publish it yet, but we've been able to write. We wrote a new paper. Basically, they came up with an improvement to that method, improvable improvement to what they did in that paper. Yeah. So their point was the homeworks were too hard, so they'd rather just come up with a new result. And that's what they did. It was a bit of a gamble, but they did. So yes, so that offer still stands. If you're able to make any, and again, I have to judge whether this is an improvement or not. But it's, I'd be happy, it's one less thing for me to grade. So I'd be happy if you actually did something that I deemed was submittable somewhere. So that's something that I know how to judge. So I'm just throwing that out there. It's possible. This one is hard though. I wouldn't try to improve this one just yet. There have been some improvements to this algorithm. This 1.5 approximation under even more special conditions on the graph. That it's not just an arbitrary metric, but it's a metric formed by a graph with unweighted edges in the graph. Then people have got this down to 1.4. So they went from 1.5 to 1.5 minus epsilon to 1.47 to 1.4 now. That's where the things currently stand. But for the general problem of an arbitrary metric, we still will not do any better with this. All right. Any other questions before we move on? Okay. All right. So as a segue to the next topic, which will be the last kind of approximation that we consider, I just want to sort of go back and recall some of the problems we've looked at, right? So we've looked at least in the regime of NP hard problems, what have we seen? We've seen vertex cover, where we got a factor 2 approximation. We've seen set cover, where we got a log n approximation. So it's an approximation that gets worse with time, with size, but it's still a bound. Okay? We've seen general TSP, where there's no approximation. And we've seen metric TSP, where again we see a 1.5 approximation. And we saw for some problems like approximate median finding and things like that, you can do somewhat better. You can get sort of very nice approximations, arbitrarily good approximations if you wish. And so the question you might ask is, for these really hard problems, these NP hard problems where we don't want to solve it exactly at all, can we get these arbitrarily good approximations? And it turns out you can. And there's a general class of problems, techniques called polytime. They're not really problems, they're not in this category. Polytime approximation schemes that give you a 1 plus epsilon approximation for any epsilon. Okay? And this is what I want to talk about next. So what is what we often call a PTAS? Polynomial time approximation scheme. The idea is that rather than saying to the user, no, I can give you a 2 approximation, don't ask me for anything better. I can give you 1.5 for TSP, but doing any better, no one's been able to figure this out for 40 years. What you say is, you tell me what error you want, I will give you an algorithm that can do it. So that's why these things are called approximation schemes. It's not a single algorithm. You can imagine it as a family of algorithms, one for each value of epsilon. Okay? And so typically what you say is that we want a 1 plus epsilon approximation. And you should think of epsilon as a very small number. That's greater than 0. So for example, you want a 1.1 approximation. So epsilon is equal to 0.1. Or you want a 1.001 approximation. You're going to get really close. Remember, 1 would be the exact answer. Epsilon equal to 0.001. And you could of course say, well, what's the catch here? I'll just set epsilon equal to 0. I'm going to get an exact answer. The catch is that the running times. So the running time is usually some polynomial in n. So it's a polynomial function of n, but an arbitrary function of 1 over epsilon. So for example, a running time of a polynomial time approximation scheme could look like n squared 2 to the 1 over epsilon. So it's exponential, but not in n. It's exponential in the error parameter. And of course now you can see why I can't set epsilon equal to 0 here. So it'll just blow up. And what this also tells you is that this sort of degrades gracefully in some sense. As you want to get a better and better approximation, you will spend more and more time. So this is a trade-off, which seems, at least somewhat reasonable. That if I want a better answer, I'm willing to spend more time on it. If I want a bad answer, I'm willing to spend less time on it. Whereas with some of these other approximations, you have either 2 or nothing. That's it. There was no chance to sort of get slightly better with more work. Here you can put in more effort and get a better answer. Unlike homework assignments where putting more effort doesn't always get you a better answer. This at least you can. This bound, of course, is what you would consider a nice bound. There are, for example, worse bounds. You could have something like n to the 10, 2 to the 2 to the 2 to the 1 over epsilon to the 50. While you would never ever in your wildest imagination call this an efficient algorithm, it is technically still a PTAS because it's polynomial in n and it has an arbitrary function of 1 over epsilon. There are things that look like this, sadly. You could even have something that's even worse. You could have something that looks like this. N to the 2 to the 1 over epsilon. Because why not? Again, this is still a PTAS, because for any fixed value epsilon, this is a polynomial in n. So in all these bounds, you assume epsilon to be a fixed constant that's given to you ahead of time, and then you produce an algorithm. So there's a technical issue. It's like a technical issue of what is considered constant, what is not. I'm not claiming this is actually efficient in a real sense, but these kinds of running times are admissible because they're still polynomial in n, they're not exponential in n. Okay, yes?
Just generalize for epsilon being pretty big.
Epsilon is big, then that's great because these numbers get really small.
Yeah.
So yeah, sure. But usually if epsilon gets very big, suppose epsilon is 10, you're saying I want a 11 approximation. You can usually do something a lot simpler. So these algorithms, they work, they'll work, but they may not, at some point there might be a simpler algorithm you can use that is not as complicated as one of these things might end up being. But yeah, sure, that'll be fine. I mean, usually, depending on the algorithm design, you'll say, oh, this works for all epsilon less than blah, or all epsilon. There might be some region where it makes sense anyway. But yeah. Yes?
When the epsilon is pretty low, how can we judge that which factor is giving the time bound?
What do you mean, which factor is giving the time?
Generally what we do, there's a constant factor, we check that log n is increasing with a higher rate or the other factor is increasing with higher rate. So in this case, we cannot say that if for this, we have some range that with this range, n square will increase with higher rate than the 2 to the power 1 upon this epsilon.
Right.
But as we don't know that what is actually this epsilon is gonna be in approximate algorithm as we give it a time. So how we judge about the time bound?
So I'm not sure I completely follow, but I think the way to think about it is there are two parts to the running time of such an algorithm. The dependence on n and the dependence on epsilon. Right? The dependence on n, on both of them you can read off from the analysis. You do the analysis of the algorithm, you'll see, okay, it depends on this quadratically, it depends on this exponentially. So in some sense you know that, okay, so if epsilon is very large, then this is the dominant term. And you can see that. If epsilon gets very small, then this starts becoming the dominant term, right? So roughly, if epsilon is, say, I don't know, around, like even 1 over log n, 1 over log squared n, say, then this number becomes bigger than this number, right? And you can substitute this in C, right? If you take, when is n squared equal to 2 to the 1 over epsilon, take logs, you get basically where epsilon is equal to 1 over log n. So anything slightly more than that, you know this is going to be the dominant term, this is going to be the less dominant. Does that answer your question? Usually we'll think of epsilon as a constant, not as something that's arbitrarily small, because when it gets arbitrarily small, if you put, for example, epsilon equal to 1 over n here, right, then this is going to be exponential in n. So you typically, you can, for some problems, you can show that you have to have an exponential dependence on epsilon. You cannot have a polynomial dependence on epsilon. There are some problems where you can, but some problems where you can't. It depends on the problem. But when you can, this is the kind of bound you expect to see. And so you can do slightly better by giving epsilon smaller and smaller, but the price you pay is running time. Okay. So we're going to look at one such example of this kind of thing. And let's take a 3-minute break, and then we can come back.
I think there is. He mentioned a couple of conferences over there saying that you should look at the conferences related to algorithms. I think it's. Wait, I'll just show you. So you see something like this, right? So you go to pages and you see project guidelines.
That's linear time.
So he says here, like, these are the conferences you should look at because these are the algorithm this one, and you can pick up the Google Scholars, they have their own website. Yeah, you just Google the conference, you look at the titles, if something good shows up, then you do the Google Scholars, type that paper title. and just look at the I think that's the best way you can use. And this website will be in our collection like last 20-25 years. So you can just look at the papers, like papers from last 25 years. So you can look at the titles.
When you say conference, then you should meet at a conference or
Yeah, it's
they meet once a year or something.
yeah. Papers are
So there's lots of breaks up front. All right, let's continue. So the problem we're going to be looking at in the context of these polynomial type approximation schemes and is a problem that you may be familiar with already. Sort of a well-known problem in this setting. It's called just curious, how many of you have heard of the knapsack problem? A quarter of you. Okay, all right. So the knapsack problem is it's a very simple problem. You can think of this as the art gallery thief problem if you want. There's also the art gallery problem, but that's a different class, a different topic. There's the art gallery thief problem. So the problem is the following: you're a thief inside an art gallery. You maybe set off the alarm. You have 2 minutes to get what you can and leave. You have all these paintings. You're of course an art thief, so you know the value of paintings. So every painting, right, every object, if you wish, has both. So there are n objects, each with a value. Let's call it VI. But they're paintings, they're heavy, right? I mean, you don't have time to cut the canvas out of the frame, so you got to take out the frame. You're stuck. So, okay? You're the thief, you have this bag, your knapsack, right? Of course, your knapsack is, it's made of some reasonable material, but it can only carry a certain amount of weight. So the knapsack carries total weight, capital W. This is also given to you. You know it, the weight of the knapsack. You bought a special one from the special art gallery thief store. What do? You have to decide quickly which items to pick to put in your knapsack so that the bag doesn't break. So find a subset of items of total weight less than equal to W of maximum value. So each item has a value and a weight. You put a bunch of items in your bag, their total weight is less than W, you added their value. That's your profit. You have 3 Picassos, a Van Gogh, Matisses, You can figure it out. This is the knapsack problem. Okay? The knapsack problem is one of these very gently NP-complete problems. It's NP-complete, but in the most polite way possible. In the sense that I can actually give you an algorithm that runs in what looks like very reasonable time to solve this problem. This is often used as a classic example of how to do dynamic programming. So if you have n items and you have weight W, there is a standard dynamic program that allows you to solve this problem. And if you haven't seen this before, I'll write it down right now. It's actually very simple. So this is of course a computer science literate art gallery thief who knows how to run dynamic programs. So the idea is that you make a big table. Okay. Let's see. So along the x-axis are items 1, 2, 3, up to n. This way. Okay. And along the y-axis, you put a line there for every value from 1 from 0, I guess, to W, the total weight of knapsack you can carry. Okay? And in a particular entry, so every entry you can think of as, so this is some matrix, let's call it M. The entry M W comma I is the best value you get with weight less than or equal to W using items 1 to I. Okay? So this entry of the matrix would store the best value you could get with weight less than or equal to W using items 1 through I. So obviously the optimal solution is equal to the entry here right? It's the best value you get with weight less than or equal to capital W using all the items. And the reason you can solve this using dynamic programming is because if you now think of, okay, what does this optimal solution look like? Well, there are two cases. Either the last item was in your optimal solution or it wasn't. If your last item was in your optimal solution, so let's say that item n belongs to opt, then opt is equal to Vn plus the best solution you can get on W minus Wn and n minus 1, right? Because you took the last item, so now you only have weight W minus Wn left, and you have to choose from the n minus 1 remaining items. So that entry would correspond to something like the entry maybe, I don't know, here. Right? It's W minus W, so you go down a bit, but you go off by 1. So that maybe was wrongly drawn. It should be drawn somewhere. Right? Because n minus 1. If n is not an opt, then what would opt be equal to? So opt would be equal to the.
W and minus 1.
One second, I think I made a mistake. No, sorry, that's correct. It'll be opt of W and n minus 1. Is that what someone said? Yeah. So in general, of course, we can say the opt solution, and that would be something like this entry right here. So opt is equal to the max. So, okay, I'll just write this here. Well, so we can say that M W comma n is equal to max of Vn plus M W minus Wn comma n minus 1 and M W comma n minus 1. And I have now essentially written down my dynamic program. You have a question? Any question? Right? So this is how, of course, we do a dynamic program. We sort of set up the optimal substructure property and then we rewrite it as an array problem. And this, of course, you can now work forwards. Since this entry depends on previous entries, you work your way forwards, bottom up, and you fill out the recursion. Dynamic programming is where you think recursively, but you implement backwards. That's what you have here. I said this was NP complete, but I just gave you a solution to this problem, and how long will it take to run? And to fill out each entry takes me constant time, because I have to look at 2 other entries and decide what to put in there. There are n times w entries in the matrix, right? So the running time right? Because it takes constant time to update each entry. So, does this seem like a problem to you? That I just give you a nice, well-behaved running time for this problem, n times w, for a problem that I said was NP complete? Does anyone see a problem here? Yeah?
Well, we need to express W in terms of the bit size.
So, is that a problem?
Well, it should be exponential then.
Why?
So, basically the table will double every time W gains a bit.
Right. So in other words, because the reason why this is not polynomial time in the input size is because my input to specify W, I need log of W bits. But my running time depends on the actual value of W, which is exponential in the size of the log W. Okay? So W is exponential, which is a silly thing to say, but it is, in log W. But log W is the number of bits needed to express W. So NW is exponential. In input size. Okay? This is what is often called a pseudo-polynomial algorithm. It will be polynomial if W is small. Which is why I meant by saying this is kind of a very nice instance of loop. It's not some, the running times are not egregiously bad, it's just that there's this annoying thing involving W. But it turns out that for problems like knapsack, often, especially problems where this value matters, you can generate an arbitrarily good approximation. Mainly by reasoning about the numbers that you use. If the numbers are what are causing you to have trouble, maybe you can somehow shrink the numbers down to some reasonable size. You can actually get an output. So it turns out you can't, well, not directly anyway, but it's not convenient to use this particular dynamic program to solve the knapsack or to build up a solution that works, that gives you an approximation. We'll use a different version of the knapsack solution, which uses a different kind of dynamic program that runs in time. So I won't tell you what it is right now, but let me just sort of stipulate that it exists and I'll explain how it works. So let V star equal to the max value, the most valuable item. Okay. So there exists an algorithm for a knapsack running in time O of n squared V star. Okay? I'm not going to tell you yet how this works. So just pretend we know what it is. I'll explain in a bit. But first notice this also has the same problem as before. It depends on the value, the max value. Again, to write on the values, you need only logarithmic number of bits in the magnitude of that value. So this is still a problem case. Doesn't make our life any simpler. It's just re-expressing the runtime in terms of different parameters, not W but V star. Okay. All right. So let's just take this for granted right now, because what I want to do now is show you how to design an approximation algorithm that is based off of this fact that you can generate this exact algorithm that's kind of expensive. And the insight here is to see that this running time seems to depend on this max value. So if I could somehow shrink the max value in some way, maybe I could come up with a better algorithm. So if I could somehow scale everything in some form, because maybe I can just scale up all the values. So if all my values were, factors of 10, and my running time depended on that max value, I could just divide everything by 10, and somehow my running time would decrease. Can I do that in a more systematic way? So the idea is going to be the following. Let's fix, so here's where the idea starts. So let's fix some number, some magic number, which I'll give you later. B. Okay? Now remember, each item had a value and a weight. We're going to ignore the weights for now, and the weights are not going to bother us at all, because the running time of this algorithm that we're going to use depends only on the values. So the weights will just be whatever they are. Okay? So let's say that we have an item, I. It has value Vi. I'm going to replace Vi. So replace Vi by Vi tilde equal to the rounded version of V. So if you think of B as 10, what am I doing? I'm rounding it to the nearest factor of 10. Right? If Vi was 25, this would give me 30. If Vi was 21, this would still give me 30. Right? So you're rounding it up. So in other words, because we're rounding it up, we know that, what do I want to say? So of course, Vi is less than Vi tilde. So Vi is less than equal to Vi. Okay. Okay? Just by definition of rounding. Because 29 becomes 30, 21 also becomes 30. So far all we've done is replace things by something larger. Right? This is going to incur error. We're going to have to worry about this error further. But let's not worry about it. Let's make one observation. The observation I want to make is that now, all my new Vi tildes, the new values that I've generated, are factors of B. By definition. I did a rounding and I multiplied by, I did a ceiling computation, I multiplied by B. So they're all, in this case, if B was 10, they're all like 20, 30, 40, 50, 60. But if that's the case, I will argue that now I can just divide everything by B. In other words, now set Vi hat is equal to Vi tilde divided by B, which of course is equal to, which I could have done up front, but just easier to reason about this way. Right? Okay. So let me make the following claim, that the solution, so the optimal solution for the Vi tilde is exactly equal to B times the optimal solution for the Vi hat. You see why? Because all I've done is scale everything by a factor of B. I haven't done anything else. I haven't moved things around. I'm not talking about the original problem yet. Okay, I still don't know how this relates to the original problem. But I do know that these two problems have essentially the same solution. Scaled by a factor of B. They're effectively the same. I don't care about one versus the other. But of course we do care, because now the instance we have with the hats has much smaller values of vi. Okay? And that's hopefully a good thing. That because the VIs are small, that we can, that the running time will be a lot cheaper. Okay?
You'd also be doing that to the maximum weight that the knapsack can carry. Right?
Pardon me?
This is just the values.
We're dividing not the weights, yeah, just the values. Yeah. So the algorithm is basically the following. So the algorithm for approximating the knapsack is the following. So step 1, replace all the VI by VI tilde. Step 2, and again, you could always combine these two steps, but I want to separate them out. Run the O of n squared V star algorithm on the instance with the VI tilde and then multiply answer by B. So does the algorithm make sense? So we had an algorithm that was exact but was somewhat expensive. So what we want to do is use this algorithm as a core but transform the problem in such a way that the algorithm is no longer expensive to run. And this is again a very classic paradigm for designing approximation algorithms. Take a problem, take a solution that is expensive but has some properties to it, and then try to get your problem to be approximated to the point where you can now use this exact algorithm on the approximate inputs. So instead of running an approximation algorithm on the exact inputs, you try to run an exact algorithm on the approximated inputs in such a way that everything kind of works out. Okay? Because it's trying to leverage something you already know about the problem, this exact algorithm. Okay, so as a design strategy, that's another design strategy you can adopt. Apart from the whole find a lower bound kind of thing, you can say, look, I have this exact algorithm. Can I somehow massage my problem to get into this place where I can use this reasoning? Okay? This is in fact a very, very powerful, increasingly powerful paradigm for designing these approximations. Because, again, to go off on a tangent, if you're doing something with large data, you might say, okay, I want to sample the data, find some small set. So yes, sample the data, find some small set, run some otherwise expensive algorithm on a small set. Because it's small, it's okay. And some more reason that this is a good approximation. Yeah?
So is n squared times v star equivalent to n times w?
Pardon me?
N squared times v star, how did we get that from n times w?
We did not. I said I'm going to give you a completely different algorithm, which I have not told you yet.
Okay.
Yeah, so we did not. It's a completely different method. Yeah. I haven't yet told you how to do it. I may not. Not today. Why is this? So again, the magic ingredient of this is the value B. So let me tell you what B is going to be. B is going to be. And this is where the magic is going to come in. So let me ask the following question now. Before we do anything else, before we worry about whether this works or not. So I told you what B is. I told you how to compute V hat. What is the biggest value of V hat star? What's the max value of V hat? What's V hat star? So remember that V hat basically is equal to Vi right? Which is equal to right? Yes? But because V star is the maximum value of Vi, this is less than equal to right? Which is up to an additive off by one thing is basically less than equal to right? Now look at the running time. If the running time is going to be, so the run time V hat star, because we're running on the V hats, which is going to be equal to n squared times the running time of this algorithm, apart from the linear time work it takes to do the transformations, is going to be n cubed divided by epsilon. Now remember how I said that the approximation schemes you're going to be seeing depend on polynomially on n and arbitrarily on 1 over epsilon. In fact, it's a very good algorithm. It depends linearly on 1 over epsilon. There's no exponential. It's a very reasonable method. The n cubed is not great, but apart from that, it's fine. So of course, as always, epsilon going to 0 will make this get larger and larger and larger. But the point here is that by choosing B carefully, and I haven't yet argued why it's a careful choice, but by choosing B in this particular way, we can leverage this exact algorithm with a carefully chosen V star to get a running time that does not depend anymore on actual values of the input. It's a truly polynomial time. The question, of course, is, well, I could have chosen B to be anything I wanted. Why did I choose that? And of course, the answer is, I chose B to be that particular value because I want to guarantee the approximation. So that magic value there is not magic. It comes as a result of trying to balance the time I want to spend and the error I want to get. And next time, we will see the analysis of how you do that. Okay? But this is the big picture is, this is all you do. You transform the input so that you can leverage some exact algorithm you had that was otherwise not satisfactory. It was too expensive. And the question now becomes, how do you transform the input? And this trick of somehow taking the input and making it a little bit fuzzy is a very, very common trick in the process. Any kind of data thing you work with, you will often, if you ever build a grid for your data and you snap points to a grid, you're doing something like this. So this is a good technique to get used to. So we'll talk more about this next time. Right? So don't forget the project submissions are due. You know, if you're in doubt, the best thing is to submit it. I will, have a day or two to go over things and tell you, and I won't. If you post something that's, not entirely reasonable, I'm not going to penalize you for having done. I think that's okay. But then make sure you do submit something today.